Okay, year 12. This lesson is all about impact forces. Describe what happens to the impact force if impact time is changed and state the change in momentum when object rebounds off a wall in a straight line and also at an angle. So, get to my next slide. Now, this has been looked at GCSE, and to remind you, this is a golfer, a professional golfer apparently, called Bill Haas. Never heard of him. There you go. And he can hit a ball, a golf ball that is, a very long distance down the fairway here. Now, he not necessarily can be the strongest person, but what he does is something called a well-timed shot. So when you bring the golf club down to hit this ball here, what he's trying to do is trying to make the impact time as big as possible. And you see that when the golf club comes down, he hits the ball sweetly, bang, off it goes, because he wants the ball to gain momentum. Now, we can analyze this by looking at the equation, which you now know, and the equation pops out here, is we know that the force multiplied by time is going to be delta mv, the change in momentum, and that's the impulse. Now, in that case then, if you make the impact time bigger, don't you make the change in momentum bigger? Also, if you make the force bigger, you make this bigger as well. But there's a limit to how much force a golfer can apply. The main thing they do work on is impact time, because these golfers are not the strongest people in the world. Therefore, what they do is they really increase the impact time to make a well-timed shot, and that's the same with tennis, etc. Other areas, we'll see this in the opposite way, is this video here is going to play a blasted, if I get damn thing open up, I bet it's going to give me a YouTube video as well. It's not working, here we go, got it eventually. The advert. But this one's really go away, horrible thing. There we go. Now, this is a cool video. You've got a bloke here and he's about to have a water balloon, which is a balloon full of water thrown at his head. What I find is quite amusing, the fact you can see he can't keep his eyes open, eventually his eyes close. But this balloon full of water is going to weigh a fair few kilograms, and in normal case, if it hit his head, it would break his neck. But when this balloon approaches and reaches his face and hits his face, the important thing I want you to notice in this video, the balloon actually wraps around his face like this. Here we go. Fantastic. It wraps around his face and eventually will burst, but it doesn't break his neck. And the whole point behind me showing you this is taking the equation the other way around. Because now, exactly what we've seen already is, getting back to my pen, boom, is we've got now the force equals the rate of change of momentum with time. And what I'm doing, well, in this case here, what he's doing is increasing the impact time, which reduces the force, because the change momentum is going to happen. This is approaching with speed v, and when he hits his face and stops, it's going to go to a final speed of 0. It's going to reduce down to 0. Therefore, the change in momentum is going to happen, but if you increase the impact time, he's then going to reduce the force. And we also can see this and applying to car crashes, and you do this again at GCSE, where if you have a car hitting a wall, you have a crumple zone here, and there's two ways you can save the person on the impact on the wall, is by making a crumple zone, gives a massive time, reduces the force, and also use airbags, which again increases time and reduces the force. And we do these at GCSE. Now, to go with that is then you can do these sort of calculations, and in this calculation here, you got a golf ball of mass 42 grams, which is straight away what we always do is we convert that into kilograms. It is struck by a club, which gives a velocity of 30 meters per second. If the contact time is 15 milliseconds, is calculate the momentum gained by the ball. Well, the initial speed of this is going to be 0, and the final speed, v, is going to be 30 meters per second. Therefore, momentum gained by this is going to be mass times velocity, because initial momentum is going to be 0. Therefore, it's going to be 0.42 multiplied by 30. And you bung that in your calculator, you end up with 12.6 kilograms meters per second. Remember, the other unit you can have is newtons seconds. To work out the average impact force, you then use F equals delta mv over t, and therefore we take our 12.6 divided by the time, and the time is going to be 15 times 10 to the minus 3, because it's going to be 15 milliseconds. And then we get hold of a value of 840 newtons. Now this one, the hydrogen molecule of 5.0 times 10 to minus 26 kilograms, moving at a speed of 450 meters per second, hits a wall and comes to rest. So here's going to be your wall. Here's going to be your hydrogen molecule. Wallops are here. It's going to go initial speed of 420. And when it hits the wall, the final speed is going to be 0. And again, what you can do is you calculate the force by using your delta mv over t. I'll leave you to do that. I previously did this, and I think I got a force of 1.4 times 10 to minus 13 newtons, but you can do that yourself. Now, the final part, what's needed, the final part of this video, is you also can get force time graphs. Now, what happens now is professional golfers or anybody at impact sport, they can improve their timing because basically get a fast camera and a force sensor in their golf club, and they can actually record the force against time as they hit a ball. And what they can do then, get these profiles coming out, and they can maximize their force time graph to get a bigger change in momentum. And like we've seen before, is F times T is going to be the change momentum, and therefore this is going to be the whole area underneath the graph. Now, to work out the area under the graph, what you do is you can do squares, which are one little square going over here, and the area of this square is going to be your 50 newtons going just over here, and then you've got your time goes across there, and that's going to be then 1 times 10 to minus 3, which is a millisecond. Now, if you can see here, the area each block is going to be 50 times 1 millisecond, which is going to be 5 times 10 to minus 2 newton seconds. You then count up your squares, and you can have here, they reckon it's going to be 9 squares in total, and that gives a total value of 0.45 newton seconds, which gives you your change in momentum. Now, the proper way to do it is actually work out the area in the graph by using a process called integration. But A-level, we just count squares, I'm afraid. Now, the last thing I want to show you is all about rebound impacts. And this is a little video where we have here of a golf ball, which is really cool. That's hitting a wall at 150 miles per hour. And you probably don't realize this, but when a golf ball hits a wall at 150 miles per hour, it completely changes shape. And because then it changes shape, it stores an enormous amount of elastic energy, and that's why it rebounds off an incredible velocity. I find that amazing. That's 70,000 frames per second. And that's what happens to a golf ball when it hits a wall. But when you got in your book, you've got this little bit here where you've got a ball. It rapidly approaches a wall, and we say this way going to that direction is going to be positive, and we're saying the opposite direction is going to be negative. Now, changing my pen color again here. What we can do then say, if it approaches the wall at speed mu, its initial momentum is going to be mu here. When it rebounds off the wall, I'm going to say it rebounds off the wall with exactly the same velocity u. When we say it's an elastic collision, it rebounds off the wall with the same velocity. Therefore, going to the wall is going to be plus mu, and rebounding off the wall is going to be minus mu. You then work out the change in momentum. We're going to have mu positive minus mu. And we know a minus makes a plus. Therefore, the actual change in momentum ends up being 2mu. And they like this sort of multiple choice questions. And what you can do is actually find out the force of the wall on the ball is going to be delta mv divided by the impact time. Now, they can get slightly more complicated because now you can actually hit a wall at an angle theta. Now, we're saying the angle here coming down with a normal is going to be angle theta, and where it bounds off the wall, it's going to bound the same angle theta. And this is where we now start looking at components, because if I'm going to resolve going in the vertical plane going here, okay, we know as the ball comes down through here, because we're looking at the vertical component, vertically is not going to be mu sine theta. But I'm saying going down is going to be a positive direction, so that's going to be positive. Now, when it bounds off the wall, it's still got a vertical component going down here, but it's going to be exactly the same what we had before of this vertical component going down. So it's still going to be mu sine theta, which is still going to be positive. Therefore, there's no change in the vertical direction. If we then resolve horizontally, and I'm going to change color pen here because I can, here we go. Because we're going to cross the angle now, is I'm going to say this way is going to be positive, and I'm going to say this way here is going to be negative. Going that way, then I'm going to have mu cos theta, which is going to be positive because resolving horizontally. Because it rebounds off the wall, isn't it now going to be minus mu cos theta? So we then look at your delta mv. Again, very similar to before, we got mu cos theta, which is going to be positive, and it's going to be minus mu cos theta. And what that then gives you is that the change momentum is going to be 2 mu cos theta. And you see that in your book. Now, the last thing I'd like you to do is, you've got these questions here. I'm going to upload them on Edmodo anyway, the answers to these. And I would like you to work through question 1, 2, 3, 4. And hopefully everything I've done already will be enough for you to answer them. Okay, hope you enjoy the video.